Good morning, class. We are looking at section 3.8 Exponential Growth and Decay. We have a lot of differentiation formulas that we should be comfortable with in order to move on. So whether it's the basic power rule, constant exponential rule, trigonometric rule, or we move into more interesting ones such as the product rule, quotient rule, the chain rule, logarithmic, and so on and so forth. Okay, so that's the first thing that we need everybody to know. Now, let's look at more coming up. All right, we put this in slide show. We've already discussed the rates of change, the average rate of change, which refers to the slope of a secant line, versus the instantaneous rate of change, which refers to the ultimately the slope of a tangent line. So having said that, here's the new stuff. Actually, not so new. Exponential growth and decay we have dealt with. So the idea of y being ce to the power of kt is nothing new. For example, a equals pe to the power of rt. There are different ways of writing them. And because of that, if you look at the formulas on the right, on purpose, I'm writing various formulas. ce to the power of kt, y sub 0 e to the power of kt, p e to the power of rt, y sub 0 e to the power of rt. So many formulas, all of them refer to the same thing, okay? Exponential growth and decay. And it follows the following. dy dt equals ky results in this equation. What does it mean? If a quantity, okay, a quantity q or q of t or y equals y of t is said to have an exponential growth or decay, if it increases or decreases at a rate that is proportional to the amount of the quantity present. So dy dt is the rate of change, and it is what? The product of some constant times the original function, k times y. So think about the concept, okay? This in turn having the following solution, okay? We've discussed the concept of a differential equation. I hope everybody remembers that. And so with that being the case, in essence, this is the solution to this differential equation, okay? And so what's happening? The rate depends on the original size. Just think about a simple example. If you're looking at the population, okay, the larger the population, the more the amount of increase, not the faster necessarily, but you know, dy dt is k times y. Now, in this case, c or y sub 0 is what we begin with, the initial value, okay? K or r, if I'm looking at pe to the power of rt, r, if I'm looking at this formula, k, if I'm looking at this formula, k, they are the same thing. We call it constant of proportionality or relative growth rate. Relative growth rate, okay? If it's positive, we have an exponential growth. And if it's negative, we have exponential decay. It's really that simple, everybody. Exponential growth versus exponential decay. So exponential decay happens when this r or k is negative. Sometimes we put that negation in the formula. Sometimes we don't. When we calculate, it ends up being negative. And it's another thing I want everybody to pay attention to. Now, this dy dt or dp dt, okay? This dy dt, which is equal to k times y, or dp dt, which is equal to kp, is the rate of growth, okay? So dp dt is the rate of growth, whereas k or r is the relative growth rate. So rate of growth, that really refers to the differentiation in essence. And I hope you remember the idea of the instantaneous rate of growth. So that is nothing brand new. I hope everybody is comfortable with that. We have seen this before. Now we are looking at it from the point of view of a calculus. So having said that, okay, look at equation 1 again. Equation 1 is sometimes called the law of natural growth. If k is positive, the law of natural decay, if k is negative. Okay. It is called a differential equation because it involves an unknown function y and its derivative dy dt or dp dt. So notice what happens. This is important for everybody to see. If you look at the right side, okay, y equals c e to the power of kt. Let us differentiate this. In essence, we go with the reverse process. Having this, let's differentiate and see what happens. If you differentiate, c is a constant. You differentiate e to the power of kt, which gives you e to the power of kt times k. I want you to see how the differentiation takes place. Okay. So if you take the k out and put the c in, it looks like this. Now what's inside the parentheses is the same as y. So I hope you see that we proved y prime is k times y. By y prime, we mean dy dt. We proved that it's k times y. In other words, if this is the solution, we differentiate both sides, we prove that it satisfies this equation. Okay, so in short, exponential growth, dy dt is k times y, exponential decay dy dt is minus k times y. So when k is positive, that it's an exponential growth. If it's negative, it's an exponential decay. The next thing I want to look at, it's called the Newton's law of cooling. When dt dt is k times t minus t sub s. Capital T represents the temperature. Lowercase t represents time. If it's equal to k times t minus t sub s, capital T is the function that represents the temperature. So minus T sub S. What is T sub S? The temperature of the surrounding. Okay, we will discuss that later on, but I'm giving you the synopsis of that. This is also following this fact that dy dt is k times y. So dt dt is k times, you can think of this as y, okay? And so it follows this idea of exponential growth and decay. This is Newton's law of cooling. So T of a T, capital T of T, becomes y sub 0 e to the power of kt. Okay, that's really the same thing in essence, plus T sub s, where y sub 0 is the difference between the two. We will elaborate on this a little bit more coming up. I just wanted to give you an idea of what's happening as far as the synopsis of the section. From here on, we look at examples that I believe you should be fairly comfortable with. All right, so let's make some sense out of everything we said. We want to look at this example. Could somebody be kind enough to read this example for us, please? Could somebody read this for us, please?
I'll read it.
Thank you.
The world population was 2560 million in 1950 and 3040 million in 1960. Assume that the growth rate is proportional to the population size. Do I keep going?
I can move on from it. Thank you so much, Joseph. Okay, so before even we move on, we are going to read this. Remember, this is a word problem. So before we move on, we're going to write the given. Okay, so we're going to write exactly what was given. So here's the given. In 1950, and we are assuming that's the initial value t equals 0, then p of 0 is 2560. In essence, if you look at this formula, this thing or c becomes that number. Okay. Then in 1960, that means 10 years later. That's why we're going to call it P of 10. When a question like this is given, the assumption is the beginning is whatever that they have given us. In this case, the beginning is assumed to be 1950. Okay, so t equals 0, P of 0 is 2560. And then P of 10, why 10? Because 1960 minus 1950 gives us 10, is 3040. Okay, so, and growth rate is proportional to the population size. I want you to pay attention to the piece in red. That really means dy dt is ky. Now, if we are using p, we're going to say dp dt equals kp. Please pay attention to the fact that the p or y or q, any variable you use, in essence is a dummy variable. It is the concept that is important. So dy dt will translate to dp dt here, because over here y is your dependent variable and t is independent. Over here, the dependent variable is p, the population. Now, can you use y? Of course, let y represent the population. It is absolutely your choice. Y represents the population, you have the same formula here. Capital P represents the population, you use dp dt. So, in essence, dp dt is k pi. That means it's following the exponential growth, okay? So that means quickly we can use this formula. The very formula up here, and we are using p instead of y, and the initial value we said is what? 2560. Think about this. Even if you replace the t with 0, this goes to 1, right? Anything to the power of 0 is 1, e to the power of 0 is 1, and it becomes 2560, and that's what we had here. The second piece of information will help us find the actual equation, and P of 10 equals 3040 is going to be used. So we are going to write P of 10 equals 3040. P of 10 is 2560 e to the power of kt. What do you replace the t with? 10. The t is replaced with 10, is 3040. This becomes an intermediate algebra equation class. You are solving for k, you are solving for exponent, and you need to do your algebraic techniques. First and foremost, get rid of 2560. So you're going to divide by it. Now, how do you get to the exponent? You undo the exponential, you take the natural log. If I take a natural log of the left side, gives me 10k, and then the right side is the natural log of that. In other words, ln of the left equals ln of the right. Ln of the left is equal to the ln of the right. So ln of the left simply is 10k. Ln of the right, you write it. Of course, you're going to simplify this and divide by 10. Now, as far as this one is concerned, class, you can simplify this further and keep it as such. Or if you are writing this, you have to write with a bunch of decimals, and you want to write as many as you can, otherwise your calculation will be off. So the relative growth, that means find the k, and we did. So now we have the formula. Okay, so we have the formula. So what happens in 1993? Well, all you have to do, go to this formula and replace the t with what? 1993 minus 1950, because 1950 corresponds to t equals 0. So 1993 corresponds to 1993 minus 1950, which is 43. So for the very first thing, notice how we arrive at 43. So 1993 minus 1950, because it represents t equals 0. You just, the rest is history. It's a simple calculation, and you come up with the answer, and everybody is happy. Okay. Rate of growth in 1993. So we got 1993 P of 43 and we done. What is the, and again, approximation, you know. What is the rate of growth in 1993? Okay, that is dp dt. Go back up here. dy dt is the rate of growth. dp dt. Now, what is dp dt equal to? K times y. So you can calculate the left or you calculate the right. So K times Y or K times P. So you want dP dt in 1993. So in 1993, you multiply the population by K. You already have found K in the previous step. So dP dt is K times pi, K times P, my apologies. So P prime of 43 or K times P of 43. This number that you found here, you put it here, and then you multiply by 5360, so 92.1116, okay? So that means in 1993 or right after 1993, the world population is increasing because this number is positive, is increasing at a rate of 92.1116 million per year. That's really the idea. So one more time, what does it mean? In 1993, the population is increasing per year by that much. So it means in 1993 or on 1993 or after 1993, the world population is increasing at this rate per year. That's the meaning of it, class, per year. So in
Professor,
1993, the world population is increasing at a rate of 92.1116 million per year. Go ahead.
I have a question about the 92.116.
Yeah,
Does that mean like it's growing by that much, like not percent, but like the amount
per
of
year.
people?
Now, that means 92.1116 million people per
Okay.
year in 1993. Does that make sense?
Yes, that makes sense. Thank you.
Perfect, perfect. So again, what it means in 1993, the world population is increasing by how much? 92 million people, roughly, per year. 92 million people per year. So people per year in 1993, okay? Or after 1993. What about the population in the year 2020? So what T should we use? Class, can anybody help us? What T should we use for the last part? T equals?
70.
Beautiful. So all you have to do, use 70. Why is that? Everybody, 2020, subtract from it 1950, and you're done. Subtract from it 1950, and you get 70. Now you put it into this equation. Take a look at this equation that we got. Replace the T with number 70, and that's what we have. Okay, this is a rough estimate. All right, we're gonna move on. So we spent a lot of time on the first question just to refresh your memory as far as what we have learned, okay? Really before, in conjunction with calculus, we want to see how it looks like. Could somebody be kind enough to read this question for us, please? Anyone? Okay. Money is deposited in an account for which interest is compounded continuously. If the balance doubles in 6 years, what is the annual percentage rate? So first and foremost, let's refresh everybody's memory about the idea of interest. Remember, for simple interest, I equals PRT. This is a simple interest, I equals PRT. So the amount would be the principal plus the interest. This is the interest, everybody. Okay. This is the amount of interest. Then A equals P times 1 plus R over N to the power of NT. This would be the compounding, where again, everybody knows A is the amount, P is the principal, R is the rate, T is the time. What is N? The number of compounding per year. So when we say annually, N is 1, semi-annually, N is 2, and so on and so forth. Sometimes, instead of P, they use A sub 0 class. Again, I just want to tell you it's the same formula. It really depends on the course and the text. And this is compounded continuously. Everybody remembers that, right? Now, should we use A sub 0 or P? It depends on the course. So let's stick with one of them. It doesn't matter as long as we understand. If we write it in this fashion, okay? P is the initial value, is the amount that we invest, principal, and A is the amount we end up with. Whereas here, A sub 0 is the initial value. Sometimes they refer to A as future value. All right, so it's going to double. So I'm going to look at it from the point of view of this question and then in general. So when it's going to double, P becomes 2P, okay? The P cancels out. And all you have to do, okay, because remember, T is replaced by 6, right, class? T is replaced by 6. In order to get to the R, just take a natural log of both sides. Left side becomes ln2, and the right side becomes 6R. So take a, okay, so let me maybe write this for you. If I said e to the power of 2, okay, I'm sorry, ln, my apologies, ln2, and ln of the right side. ln of the right side becomes 6R. So R is ln2 divided by 6. Now, ln2 divided by 6 is the precise answer, everybody. This is the precise answer. Now, this is a rough estimate. Normally, we want it in percentage. Okay, so what I want to do, I want to remind you of this concept of doubling. So remember what we have seen before. The concept of doubling in general, if I want to look at this formula becomes this formula. You see that, everybody? And I'm not going to replace the T. So from here, 2 becomes e to the power of RT. Now, if I take the natural log of both sides, I get ln2 equals RT. So I want everybody to pay attention to what happened. I'm taking a natural log. If I solve for R, I get ln2 divided by T. If I solve for T, I get ln2 divided by R. You can, after we prove this, you can use this formula. So let me tell you what each one says. So doubling time, okay, doubling time ends up being this class, ln2 divided by R, okay. The rate for doubling time would be ln2 divided by the time that it takes to double. So take a look at this formula. That's in essence, look at this top formula. ln2 divided by what? time. What was the time? 6. So what we did here, we proved it in general. So it makes it easier to use the general form. Okay? So I hope everybody's clear on that. By the way, if I go with the half-life, it works absolutely in the same manner. Okay, you just put 1/2 on this side and you work it out. Okay. All right. Physicists express the rate of decay in terms of half-life, the time required for half of any given quantity to decay. So I just went over the doubling time and I showed that h was ln2 divided by k. The half-life gives you absolutely the same thing, class. You can go through the process and see that. The only thing I want to make a note of, it depends how you write this. If you write the function this way, the process works out that it gives you this one minus ln2 over k. If you write a decay with a negative k, remember, we said when k is negative, it's an exponential decay. Some texts, they put a negative sign and they keep the k as positive. Some texts, they do not, just they write the k. So this is the same for exponential growth and decay. Now the value of k positive means it's exponential growth. Negative means exponential decay. So they use the same universal equation and the k dictates what we are dealing with. Some, they want to make sure that it's written negative. How do you write it? It's absolutely up to you. So one formula that is in use, m representing the mass at time t equals m sub 0. That means representing the mass initially e to the power of kt. Now, again, e to the power of kt or e to the power of minus kt, it's ultimately your choice, if you will. It depends on the text, but you got to be very smart and understand when to use what and what it means. Again, if you're using this for exponential growth, k will end up being positive. For decay, k will end up being negative. If you're using this one, you're using it only for exponential decay, and you put the positive k here because the negative sign is given to you. So here's the question. A sample contains 1 gram of radium. How much radium will remain after 1,000 years? We know the half-life is 1620. Okay. Any formula that you want to use, okay, you put it there. Okay, c e to the power of kt, c to the power of minus kt, m of t equals m sub 0 e to the power of kt. Choose, doesn't matter. The half-life is 1620, and we want to know what happens in 1,000 years. Y of 1,000 is of interest to us. So let's work it out, see what happens. Half-life is 1620. That means if you have the initial value of c, that's why in some cases they use y sub 0, or in this case m sub 0. It makes it a tad easier to follow and understand, but it is fine. So if you're sticking with this formula, half-life means what? The c, which is the initial amount, goes to half of the original size. That's the meaning of half-life. Now you cross the c. Okay, everybody? And you end up with 1/2 only on the left. Now, if you take, look at the right side. The right side is e to the power of something, 1620k. So if you take the natural log of both sides, you practically solve this. Natural log of the left is equal to the natural log of the right. Okay, the right side becomes 1620k, and the left side becomes ln1 minus ln2. Okay, what is this one? ln1 is 0, so negative ln2 divided by 1620. So notice what happened. We kept the k, everybody. We kept the formula with the positive k. The process will give us the negative we are looking for, okay? Minus ln2 over 1620, okay? Of course, instead of 1620, if you put the t, you can find the general format. I'll see if I can discuss that with you in a moment, but hold on one second. So minus 0.0004279, and so this is your formula now. So notice we do get this negative in the process. It must be negative for a decay. So what do you want? Y of 1000. Everybody replace this t with what? 1000 and observe. Okay, it's a simple case. And that's your final answer. Okay, everybody? So this is what we get. If we wanted to find the half-life in general, it works out the same way. And that, as I mentioned, for this one, we end up with minus ln2 over k. Okay. So right here, if you had kept this as a t class, if you had kept this as a t, then you would get ln of 1/2 is ln of what? Okay, kt, which becomes, this one becomes kt. If you, again, if you didn't replace the 1620, everybody, okay, if you didn't replace the 1620, so that means what? That means this is equal to kt, and the t, okay, it's what? Minus ln2 divided by k. Now this t class, in some cases they use h, which means half-life. Okay, half-life. So I hope everybody's comfortable with that. All right, we're gonna look at this one. Anybody feels like reading this question for us, please? Next question. Can somebody read this one for us, please?
Suppose that 10 grams of the plutonium isotope Pu-239 was released in the Chernobyl nuclear accident. How long will it take for the 10 gram to decay to 1 gram? Pu-239 has a half-life of 24,100 years.
Thank you so much, Ethan. Again, we want to translate what's given. Okay, so first we decide which formula we use. Okay, we are using this one or that one, because if we use this one, minus ln2 over k, if we are using this one, ln2 over k, so on and so forth. So we use one of them, and it's absolutely up to you. I can't emphasize this enough. It is up to you. And here's the given, everybody. So we use one of those formulas, the top one. Originally, we have 10 grams, okay? 10 grams, that's the original amount, the initial amount, C, Y sub 0 or C. And the half-life is given to be 24,100 years, okay? So how long does it take to go down to 1 gram? The amount becomes 1 gram, okay? So first and foremost, we need to come up with this equation class. So y equals c e to the power of kt, we need to come up with that. So we have a choice. We've already done that. We can go through the process of finding k, okay? Or take a look at this formula, and I want everybody to see this formula, class. If you look at this formula, this also tells you k equals minus ln2 over h, where h is the half-life. You can use that. Again, you can only use it after you've proved it. We've gone through the proof class. Or we go through the process. I want to quickly show you both. So if we go through the process, half-life, okay, half of c is c e to the power of k times t. We said t is 24,100. Class, this is 24,100. Let's just, this is 1. Okay, this is number one. 24,100. That's a typo. 24,100. And by the way, I think the next line show that. Okay, so 24,100. That's a typo. I want to make sure it's clear that this was a typo. Get rid of the constant. And notice, okay, we have it right here, 24,100. So somehow it was wrong. In any event, you take a natural log, okay, okay. And of course, remember, ln of 1/2 is ln1 minus ln2 or minus ln2. Okay, we've gone through that. Okay. And so we can find k from here to here. So k is found. Remember, this one class is minus ln2, and k is minus ln2 over 24,100. Or, as I mentioned, we could have used minus ln2 over h. Either way. Why could we use that? Because we have already proved it. So if that's the case, this is y of t. So we want to see when we get to 1. So take a look at what happens, everybody. Y of t is replaced with 1. Again, this we have done in algebra class. This stuff is really not brand new. We've seen it in algebra. Replace it with 1. So when you replace it with 1, you divide by 10 and you take a natural log. So you divide by 10 and you take a natural log. When you take a natural log, the left side becomes ln of 0.1. The right side, when you take a natural log, just gives you the exponent. So what is t? ln 0.1 divided by negative 0.000028761. And I put a lot of decimals because we really need that, everybody. It's important to see the number is extremely small, k is extremely small, and if you don't carry a lot of decimals, you will get to a wrong answer, okay? And so t becomes over 80,000 years. Okay, 80,000 years. So the concept of a half-life, we have seen it in algebra. We are repeating the same thing that we have seen, okay? There's really not much brand new stuff here. All right, now, the population of bacteria grows from 1,000 to 4,000 in 3 hours. Assume exponential growth. That means the formula at the top, okay? That means dy dt is ky, and that's why we end up with that. So we want to find the population in 6 hours, and when will it reach 30,000? So if we are using the formula at top, okay, originally we have 1,000, okay? So originally we have 1,000, so that's the original size, y sub 0 or c. And then in 3 hours, when t is 3, we have 4,000. So this is the information given. If we use this formula, c is 1,000. Y of 3 is 4,000. Now first, in essence, when we want to find the population in 6 hours, we need to find the k. In other words, we need to find the formula. And therefore, in 6 hours, that's how we get to part A. And then part B, at what point is 30,000? So pay attention to what happens in part A. First, you need to find the formula. Then you plug in 6. To find the formula, that means what is missing? K. Okay, so K is missing, everybody. So how do we find that? Very simple. C is replaced with 1,000, and then you write y of 3. So C equals 1,000, so this is the formula, and then y of 3 means 4,000, okay, equals 1,000 e to the power of k. So I'm going over this very fast because it's basically intermediate algebra and we should be comfortable with it. So one more time, this is the formula with initial size. 3, you replace the t with 3, it's 4,000. Drop the 1,000, divide by 1,000 and you get 4, you get e to the power of k times 3 or 3k. What is the next step? Natural log. So take a natural log of both sides. This becomes ln 4, this becomes 3k. So ln 4 equals 3k. So k is ln 4 divided by 3. If you keep it as ln 4 divided by 3, it's a precise answer, class. And you can stick with that. So this is the formula. Okay. And now for part A, in 6, replace the t with 6. Okay, simple calculation. I wouldn't worry about that too much. So replace it with 6. The next one says, okay, when do we get to 30,000? Well, here's the formula, everybody. Put 30,000 on the left and solve for t. So you drop 1,000, that means you divide. You get to this one. Take a natural log of both sides. The left side, ln of 30, the right side becomes the exponent only. So ln of 30, 0.4621 t. So what is t? Ln of 30 divided by 0.4621, which gives you 7.36 hours. I hope everybody is comfortable with that, class. Okay. This is the exponential growth. I'm going to quickly show you something you've seen in algebra class, but in case you forgot, this is another approach, and sometimes it works better when you want to come up with a better approximation. So let me show you something. Okay, so we got ln 4/3, right? So look at y of t. So if we go from here and we write down up here, y of t equals 1,000. E to the power of, instead of writing 0.4621, I'm going to put ln 4 over 3. T. If you write it this way, it gives you a better approximation. Here's another way of simplifying this. So take a look at what I'm going to do. I can write this as 1,000 e to the power of ln 4 to the power of 130. I hope everybody understands what I'm doing. I'm just playing with the number ln 4 over 3 times t. I can write it in this fashion. So when I do that, notice what happens. (1,000) times 4 to the power of 130. This is another way. You can try this, and you see that one gives you the same answer. I just wanted you to remember some of the stuff we did in algebra, okay? All right, perfect. Newton's law of cooling, okay? Let's quickly read that. This is interesting, class. First, we discussed dy dt equals ky, y becomes ce to the power of kt. According to Newton's law of cooling, okay, It states that the rate of cooling of an object is proportional to the temperature difference between the objects and its surrounding, provided that this difference is not too large. This law also applies to warming. Think about the concept. You have a cup of coffee, you bring it to the room temperature. Everybody knows that this cup of coffee is hot and or very warm, and it's going to cool down. And ultimately, if you leave it in the room, ultimately in a long run, takes the temperature of the room. It's very straightforward. You have a beverage that it's room temperature, you put it in a fridge, it's going to start cooling down, and eventually it takes the temperature of the fridge. So that's the idea of a surrounding, okay? The effect of the surrounding. And it has got to do with the fact that the surrounding is much, much larger than the object, and therefore it takes over. So if we let capital T of T, capital T represents the temperature, lowercase t represents the time, capital T of T be the temperature of the object at time t, and T sub S be the temperature of the surroundings, then we can formulate what we call Newton's law of cooling, okay? So remember, dy is ky. Now dt is k times the same thing, y, but depends on what? Remember, I want to go back to this. I want to remind everybody what happened here. The rate of change depends on the population y, right? Now the rate of change here depends on the difference between the two temperatures, okay? Proportional to the temperature difference between the object and its surroundings. Capital T minus T sub S. Again, T sub S is the surrounding temperature. K is a constant. T sub S is the surrounding temperature, and K is the constant. So it's important for everybody to understand what we are looking at here, class, okay? And so having said that, let's write the formula as follows. So dy dt, we're going to change it to dt dt. Ky, we will change it to k times t minus t sub s. So we take t minus t sub s to act like a y. Okay? So that's what's happening. Now we want to differentiate this. Take a look at this one. If I want to differentiate this, the derivative of y is y prime, the capital T is t prime. What about t sub s? T sub s is the surrounding temperature, and it's a constant. So the derivative is 0. Okay? So I want you to understand that when you differentiate this, this gives you 0. So I hope everybody's comfortable with that. So y prime is t prime of t minus 0. You can think of it in essence, let me just write that. You can think of this as minus 0, okay, which we don't write. So dy dt, is ky, the same thing we had there. So what is y? T minus t sub s. So if we go back here, okay, we can rewrite it as follows. T sub t minus t sub s is y, or y of t, or y sub 0 e to the power of kt. So I want you to pay attention to the blue one, everybody. I want you to pay attention to the blue one. Y is the same as y of t. This one is being repeated, and then this is the right side, y sub 0 e to the power of kt, or y sub 0. Please understand, class. Y sub 0 here, or y of 0, or y sub 0. Ultimately, they refer to the same thing known as the initial value. So having said that, okay, so y of t is capital T of t minus t sub s, okay, and if we go with that, whereas here is y of t is e to the power of kt plus c, or e to the power of c times e to the power of kt, or y sub 0 e to the power of k. This is just the way you would write that. And y sub 0 is e to the power of 0. Stick with this formula, class. Stick with this formula. Okay. And so what do we want? We want this one. Take a look, class. This one, what we want. So what do we do here? Take a look at the blue one. Take a look at the blue one, minus t sub s. Just move it. Make it plus t sub s. So take a look. Minus t sub s. Move it and make it plus t sub s. Okay? Plus t sub s. Okay? Now, as far as you're concerned, class, you can use this formula. Okay? Now, the discussion for the Newton's law of cooling becomes more apparent when we look at integration, okay? Because the anti-differentiation will give you the answer. So take a look. You're going to use this formula. Capital T of t is y sub 0 e to the power of kt plus t sub s, where t sub s is the surrounding temperature. But what is y sub 0 is the initial temperature minus the t sub s, okay? And why is that? All you have to do, just replace everything with 0 here. So I want to quickly show you something. Let's see, let's use it. If I write t of 0, everybody, then we have y sub 0 e to the power of k times 0, that means 0, and then plus t sub s. I hope everybody can see what I'm doing. In this formula, replace the lowercase t with 0. That's what you get. Okay. Now, t of 0 is the same as t sub 0. E to the power of 0 is 1, so this is y sub 0 plus t sub s. So what is y sub 0? Y sub 0 is the change in the two temperatures. So I hope you see, in essence, the proof as to why y sub 0 is always the difference in temperatures. Okay? Class, y of 0 and y sub 0, they refer to the same thing, the initial y. T sub 0 and T of 0 mean the same thing. Okay, so having said that, could somebody read the question so we can go over it? Could somebody be kind enough to read this question for us, please? Anybody? Okay. A bottle of pop at room temperature, which is about 72 degrees Fahrenheit, is placed in a refrigerator where the temperature is 44 degrees Fahrenheit. After half an hour, the soda pop has cooled to 61 degrees. Okay. So what is the temperature after another half an hour? And how long does it take for it to cool to 50 degrees Fahrenheit? The very first thing we need to do is write the given and then come up with the equation at the top, capital T of t. That's what we need to come up with. In order for you to come up with that formula, make sure everybody understands what we are doing. Class, you got to come up with this formula, which means you got to come up with y sub 0, you got to come up with k, and come up with t. That's the meaning of it, okay? So let's read the question again. Quickly, a bottle of soda pop room temperature is wherever you place it, that's your surrounding. It is placed in the fridge. So that's T sub S. This is the surrounding now, class. Okay. So what is 72 degrees? This is T of 0 or T sub 0. Initially, it's at 72 degrees. So this is T sub 0 or T of 0. This is the surrounding temperature. So we have showed that y sub 0 is T sub 0 minus T sub s. Their difference is y sub 0, class. Their difference, 72 minus 44 is y sub 0, which is 28. So what do we have? We have the initial temperature, T of 0, T sub 0. We have the surrounding temperature, and their difference results in y sub 0. Okay. We also have, after half an hour, we can go with 1/2 or we can go with 30. Let's go with the minutes. So T of 30 is 61 degrees. So let's write all of this. T sub s is given. T sub 0 is given. T of 30 is given. And we just said their difference, okay, 72 minus 44 equals 28 is y sub 0. So now let's write the formula one more time. T sub s, by the way, you put the T sub s first or at the end, it doesn't matter. 44, so remember, plus 28 e to the power of kt. So there are three pieces we are looking for, everybody. There are three pieces. We are looking for k, we are looking for y sub 0, we are looking for T sub s. So quickly we found y sub 0 and T sub s. So what is missing? K. How do you find it now? This piece of information. This piece of information, T of 30 is 61. So T of 30 is 61. Replace the T with 30. And the other side is 61. This is a simple calculation. So take a look. Now becomes pretty much intermediate algebra. So T of 30 is 44 plus 28 e to the power of k times 30. Okay. So first and foremost, you are going to subtract 44, okay, from 61. And then you're going to divide by 28, and you're going to take the natural log. Okay, I need to do a couple of steps in between for you. So let me do that. Number one, 44 we subtract this and we get 17. So that's the first one. So minus 44. Okay, so the next step, E, we're looking at this one. The next step, E to the power of 30k is 17 over 28, everybody. The next step is taking a natural log. Now I'm going to take a natural log. So I'm going to take natural log of each piece. So when I take the natural log of the left side, I get 30k, and the right side, ln of 17 over 28. I divide by 30, that becomes the k. So I hope everybody is clear what happens. Now the formula capital T of t is all completely known. Okay, so the very first thing is to find this formula, everybody. The first thing, find the formula. We got it. Now part A, what is the temperature after another half an hour? That means the lowercase t is now 60, class. So I don't want you to be confused that it's T of 30. No, we had T of 30. Now another half an hour, that means in an hour, total of 1 hour. So T of 60. And you calculate it, big deal. Okay. Part B, how long does it take for it to go to 50? Now set this one equal to 50 and solve. Set it equal to 50. Now this, again, you've seen it many times. Subtract 44, okay. subtract 44, right? Subtract 44 and you get 6. Divide by 28. Take a natural log of both sides. So if I take a ln of this equal to ln of that, then I get negative 0.016631 equals ln of, I can say it's ln of 6 over 28. I can say ln 6 minus ln 28. It doesn't matter. Okay. This has a t. I forgot to put. So let me actually fix this. Doesn't look. So t equals natural log of 6 over 28. So natural log of 6 over 28 divided by this number, negative 0.016663, that results in t with a bunch of decimals. By the way, 92.6 minutes. That means 1 hour, 32.6 minutes, or 1 hour, 33 minutes. All of them is approximation. Because it's all approximation, you can go with 1 decimal or none. But when you're doing the work, make sure you follow the instruction. Okay, class? You want to follow the instruction. So, I hope everybody's clear as to what happened. Let's look at another example to make sense. To make some sense out of this, Newton's law of cooling. Should I ask anybody to read this one for us? Anybody feels like reading for us, class? Okay. A 180-degree turkey is removed from the oven and placed in a 74 degrees Fahrenheit room. After 15 minutes, it has cooled to 136 degrees Fahrenheit. We want to find the general solution. And that's, even if they don't ask for that, we should always do that. And then how long does it take to cool down to 110 degrees Fahrenheit? So let's see what is given. I hope we can read and understand what's given to us. So 180 degrees, it's the original temperature, is T of 0 or T sub 0. We're going to bring it somewhere. Where do we bring it? We bring it to where the temperature is 74 degrees, and that is called the surrounding. So we bring it to the room of 74 degrees Fahrenheit. So this is T sub S. So recognition of the initial and then the surrounding. After 15 minutes, so T is 15. Okay, that means capital T of 15 becomes 136. So let's write all the given. Okay, so the surrounding temperature, the room temperature is 74. Originally 180 degrees. Okay, 15 minutes later, 136. So right away, we said Y sub 0 is T sub 0 minus T sub S. Their difference of 106 is Y sub 0. The difference of 106 is Y sub 0. So having said that, we have the formula. Okay. And now we use the fact that T of 15 is 136. T of 15 is 136 to find the K. So T of 15 is 74 plus 106, e to the power of K times 15 equals 136. Now, I'm going to assume you can finish the job. Subtract the 74, divide by 106, take a natural log. So there are a couple of steps here. I'm going to leave it for you to finish it. You can do that because I've done a number of those, and this is all intermediate algebra. So from here to here, there are a couple of steps, class, okay? So that shouldn't be a problem. Of course, just 74 subtracted gives you 62. Okay. Let's e to the power of 15k is 62 divided by 1. By the way, we know 62 and 106, they have a common factor we can simplify, but I kept it like that. So you can see that if you take a natural log of both sides, again, I did that, and then from here, you get to this answer. And that's the formula, okay? And so finally, how long does it take for the turkey to cool down to 110? Replace it with 110. So this one, replace it with 110, okay? Subtract 74, divide by 106, take a natural log, okay? So again, okay, that's what you get, okay? So divide by, so, and then of course, 36 divided by 106. So this step is just after that, you get this step. Now take a natural log of both sides. If you take a natural log, what do you get? Negative 0.0357554t equals ln 36 over 1. I didn't even simplify on purpose because I want you to see where the numbers are coming from. And of course, you can even say ln of 36 minus ln of 106. But in any event, divide by negative 0.035754, and you have your time. Okay. This is the Newton's law of cooling, and this is it, class. Can somebody read this question for us, please? Anybody feels like reading this?
I can read it, Professor.
Thank you.
A dead body was found at 1:30 a.m. when the temperature was 55 degrees Fahrenheit and the body temperature was 87 degrees Fahrenheit. Normal body temperature is 98.6 degrees Fahrenheit. 1 hour later, the body has cooled to 85 degrees Fahrenheit. One of the three suspects, Scrooge, had an alibi for 9 p.m. and after Claudia has an alibi between 8 p.m. and 9:30 p.m. and Sam had an alibi until 11 p.m. Who has a good alibi?
Thank you so much, Zainab. See, I'm sure you guys have watched CSI and I don't know, Criminal Minds, things of that nature. Put on your detective caps. We are not going to go over this. I want you to do this on your own at home. You have enough practice with this stuff, but believe it or not, the purpose of this question was to tell you things we study, they put it into a good use, and they definitely use this part to find the guilty party. Okay, this is it. I'm expecting you to finish this on your own and be able to handle it, class.